you'd like to start the recording, that would be great. And
Yeah,
understand that people may join us in a minute. So a very warm good afternoon and also good morning to our national and international colleagues for the November Impact Research Seminar Series. And thank you to today's presenter, Dr. Luca Brombal, a researcher from the Department of Physics at the University of Trieste in Italy. So Luca gained his PhD on X-ray phase contrast imaging in 2020 from the University of Trieste in combination with the National Institute of Nuclear Physics, Electra, and the University of College London. He received in 2021 a Young Researcher Grant from INFN to design, build and develop a new compact multimodal phase contrast and spectral imaging system. And from October this year, Luca is a researcher at the University of Trieste, a lecturer in radiation protection and a leader in his photon counting edge illumination phase contrast imaging project group. That's a super long name, Luca. But today you're talking on spectral and phase contrast biomedical engineering from synchrotron sources to laboratory setups, and it's over to you.
Thank you very much, Sarah, for the nice introduction. So let me see whether I can share my screen. I hope you can see the screen. Is that all right?
Yep. Yeah.
Yes,
okay.
Thank you. That looks great,
So,
Luca.
Thank you very much for the introduction, and I'm really, first of all, really happy to be here with you. So yeah, as Sarah pointed out, it's quite early in the morning, so I might still be sleepy. So please feel free to interrupt me if I say some stupid things. It might happen during the seminar. But what I'll try to do is to speak a little bit about spectral and phase contrast in biomedical imaging, both giving examples of application at synchrotrons and with laboratory setups. But as you might know, this title is actually too broad. And so I'll try to find a path in these fields. And of course, this is not the only path or the right path. It's just what we have been following in the recent years here in Trieste. So this is the outline of my presentation. Okay, sorry, let me get the laser pointer. Okay. This is the outline of the presentation. So first of all, I'm going to introduce a little bit of physics background, but I promise I'm going to be fast and with as few formula as I could. And then the talk is going to be split in two. The first part with X-ray imaging, X-ray spectral imaging, sorry, both at the synchrotron and at the lab. The second part is going to be more on phase contrast imaging, with examples also here at the synchrotron and at the lab. And the last part, I'm happy to introduce the PEPI lab. That's a new compact spectral and phase contrast imaging tool or small facility we are developing in Trieste. So the physics first, I'll be brief on that. But so when talking about both spectral and phase contrast, and I think you know this very well, it comes in handy the wave model for interaction of X-rays with matter. And in this model, as you know, the effect of the presence of the sample on the incoming X-ray wave is basically a modulation of the outgoing wave, both in amplitude due to attenuation effects and in phase due to phase shifting imparted by the sample. And they find these kind of formulas very handy because it gives you the idea of both the contrast sources in spectral imaging, so attenuation and then spectral imaging, which is the modulation in amplitude basically, and the source of contrast of phase contrast imaging, that is the modulation in phase, of course. So why do we need phase contrast and why do we need spectral? And for sure, for phase contrast, all of you already know that, that for soft tissues and energies of radiological interest, phase effects are much larger than attenuation effects. So in a nutshell, phase contrast we need because we need to increase visibility of soft tissues with X-rays. On the other end, why do we need spectral imaging? We use spectral imaging because the dependence of attenuation with energy is much more interesting, let's say, with respect to the dependence of non-phase on energy. And by using the different dependence of different elements, especially when you increase the atomic number of elements, for instance, if you inject iodine in a patient, well, by exploiting these differences in the attenuation coefficient, you can really separate and quantify chemical elements. So basically, you have chemical information through spectral imaging. So that's why we might want to use both techniques. So we're going to start now with spectral imaging a little bit, with a couple of principles, and then to implementations and applications. So spectral imaging, acquire spectral images basically means acquiring at least two images at different X-ray energies somehow. So in the pretty standard example where we have a sample with iodine inside, as in this case, here we have 5 cuvettes, some of them containing different concentration of iodine. The most clever thing to do is to acquire 2 images at energies just below and just above the iodine K edge, where there's this jump in its attenuation coefficient at 33 keV. And by using these 2 images as inputs to our decomposition algorithm, what we can get as output is a decomposition map, where you can extract the actual density of your contrast medium, in this case iodine, and of your embedding medium, in this case water. So uncoupling basically these 2 elements within your object. Also, the water image is sometimes in clinics referred to as the virtual non-contrast image, because basically you get rid of the contrast medium virtually, and the iodine is of course the contrast medium image. And so, of course, spectral decomposition is a crucial step in the spectral imaging pipeline. But mathematically, it's very easy to describe as well. So the only thing we need to do is to choose 2 basis materials that are reasonable, in this case water and iodine, and express our low and high energy images as a linear combination of these 2 basis material bases. And in fact, this turns out to be a linear system, very simple, and you can invert the system. And by inverting the system, you get the density maps, for instance. And so in principle, basis material composition is very straightforward. And since you can do it with 2 energies, it's also straightforward, its extension to multiple energies. So let's say we have an object containing different contrast media, for instance, iodine, barium, and gadolinium. Probably here it's barium and gadolinium are the other way around. Sorry about that. And if we acquire multiple energies in this case as inputs, so we acquire images at different energy channels, we can basically present the same problem, but with a bigger matrix, with n energy channels and m materials, provided that the number of materials is smaller or equal to the number of energy channels. And therefore, even in this case, mathematically invert the matrix. So to get multiple material maps, and we're going to see an example in a minute. The only problem with this is that usually using this inversion, you really boost image noise. And so you need to take care of that. And here we see a couple of examples I found in literature, both for in terms of micro CT. So here we are talking about small objects, okay, micro CT or micro radiography. So we have an example. Actually, this was acquired at our lab with a mouse injected with iodine-based contrast medium, where we could separate, of course, bones and vasculature. We have examples of barium that has been used, for instance, in this case, to estimate the uptake of barium within joints, and also joint use of iodine and gadolinium in some tumor model of rats. So yeah, of course, we have got plenty of examples of spectral imaging. But how do we acquire these two images at different energies, basically? Because we need that input, right? So we need at least those two images. And there are many different systems allowing you to do that. Those of you who work in clinics are for sure familiar with this that I call X-ray spectrum-based spectral imaging systems, where basically you have, in this case, we are talking about CT scanners, and you need to have two images at two different X-ray spectra. So there are different arrangements for different companies, but either you can get a dual source with two different energy spectra, or a single source with a fast voltage switching, or you can even have a dual layer detector where the first layer hardens the beam and the second layer basically records the hardened beam, so you get two spectra. So this is done in clinics, and this is not what we do. What we do is something that is coming actually also in clinics, and is detector-based pixel by pixel energy discrimination. And for doing that, you need a chromatic detector where each pixel for each event can group the photons and count the photons in different energy beams, so giving in a single shot the energy information. Most of them have two energy beams. Or if you are even fancier at the synchrotron, you can use crystal-based energy dispersive systems based on bent crystal. And this is a sketch of the system we have now at the CIRME beamline at the electrosynchrotron. And of course, I'm going to talk about these two setups, basically. So let's start with crystal-based spectral imaging. So what we could do at synchrotrons. And let's start with a simple sketch of how a synchrotron monochromator or beamline works, let's say. So, of course, as you might know, the synchrotron generally produces a polychromatic or white beam, and you need to extract some specific energy, which is what, for instance, you do for breast CT, of course. And for doing that, you use a monochromator crystal that in this case is called the Lowy crystal because it's in transmission geometry. And according to the angle of the crystal and according to the Bragg's law, you by rotating this crystal, you pick different energies from this polychromatic white beam. But this is not sufficient for doing spectral, at least not single shot spectral, because you just pick one energy, and we know that we need at least two. So one way is to bend the crystal, and by bending the crystal, each different position on the crystal is gonna satisfy the Bragg's law at a different energy. So basically here you generate a fan of energy and or what is called an energy dispersed X-ray beam, which is dispersed in space, and then due to the focusing properties of a bent crystal is gonna be focused somewhere downstream, and then it's gonna diverge again onto the detector. The trick is to position the sample at the focus, so you have the same portion of the sample that is illuminated by many different energies at the same time, and then these energies, they diverge on the detector. So you map different energies at different spatial positions on the detector. And by tuning the bending radius, you can tune the bandwidth of your system, and you tune also the geometry of your system. And so you need, you have a couple of free parameters to play with to optimize the system. And of course, if you, let's say, tune the system in order to have this energy bandwidth across one or more K edges, you are in for spectral imaging. So this is the setup that actually we've implemented at CIRME. So we've got the white beam coming in for sure in the beamline. This is the experimental arch, so the one before the patient touch, let's say. We have the white beam coming in, and this is the most important piece. So this is a bending frame where we position our silicon wafer. So this is our monochromator, basically. And this guy here is bent, and we bent it quite a lot to 0.5 meters. That, I mean, you could really tell it's bent also from the distortion of my face here. And then, of course, somewhere downstream, you position your sample, and we detect the X-rays on a Pixel 8 detector. And so this is what an image looks like. So in this case, we've got in the field of view 2 cuvettes, one filled with iodine and the other one filled with xenon. And the reason is quite obvious, but I'm going to tell you in a sec. And the good thing is that by bending this much our crystal, we could achieve an energy bandwidth covering 2 K edges simultaneously. So in this image, we are looking at position on the horizontal axis, but at energy on the vertical axis. So we achieved 5 keV energy bandwidth, which is the largest so far at this particular energy. And in this way, we could bracket 2 K edges simultaneously. And of course, since we've got a so big energy bandwidth, we decided to target 3 K edges simultaneously of 3, let's say, clinically or biologically relevant contrast agents. So iodine, barium, and xenon, and we performed tomography with that. And here we are still in the phase where we are doing a feasibility test with simple cuvette. But you acquire all the images, all the projection, you perform tomographic reconstruction, then multi-material decomposition, and then you end up with a slide, so with a tomographic view of your sample, where you could uncouple 3 materials, so all the 3 contrast agents plus the embedding material that in this case is water or plastic. It really doesn't make a difference. So our goal is to perform simultaneously cardiovascular, that's why iodine, respiratory, that's why xenon, and inflammatory or gastrointestinal imaging, that's why barium. On the other end, we have also a setup for detector-based spectral imaging, and this you can apply, of course, with conventional X-ray sources, as in this picture. This is our new lab. At least this was our new lab. Now it's much better. And you can also apply it at the synchrotron with pink beam, provided that you filter the beam quite a lot. So spectral detectors can acquire images over multiple different energy channels in a single shot, as I told you before, and they must fulfill a few requirements, let's say. So they must have high Z sensors, because we want to be very efficient at energies of interest. So high Z sensor basically means cadmium telluride or cadmium zinc telluride or gallium arsenide. These, I think, are the biggest player. And they need to be small pixel if we want to do small animal images as we want to do. So if we are going to micro CT or preclinical studies, they should feature small pixels. But if they feature small pixel, they must feature also charge sharing compensation mechanism as well. This is crucial for spectral response and for spectral imaging application that otherwise is completely, let's say, overwhelmed by the sharing of charge among close pixels. And here I've listed a couple of detectors that have at least a few of these characteristics. So that's for sure detector based on Medipix 3. There's Pixel Pixie 3, that's what we are using. There are direct conversion devices. There's of course detectors Eiger detector that I think you guys are using. But adding the detector is not enough. You really need to characterize your system very well to extract quantitative and good quality spectral information. So you need to, of course, have a good estimate of your object composition, but that's easy. And you really need to have a good estimate of your X-ray spectrum. And this is relatively easy, let's say. The trickiest bit, at least in our experience, was to have a good estimate of the detector response. So the spectral response you expect from the detector. And for characterizing it, we actually brought the detector to a couple of synchrotrons, acquired many monochromatic imaging experiments. And as you see in this case, for instance, this is the spectral response of the detector to a monochromatic beam of 37 keV. So it's not monochromatic at all, the response. And you have a lot of features due to the sensor material and so on and so forth. So you really need to characterize it. And once you characterize it, then you know its response. So the probability that a photon of a given energy is detected in a given energy beam. When you put everything together, you have the full picture of your spectral system, and you can use this full picture to compute the material decomposition matrix, which in this case is a weighted average of the attenuation coefficients over the spectrum and the spectral response of your detector. And this we have been doing for quite a while in Trieste, and we try to perform some not so trivial experiment in terms of spectral decomposition by performing quantitative multi-material micro-CT with a PIXIRAD. Of course, PIXIRAD has two thresholds. So to acquire 8 energy beams, in this case, we had to repeat the acquisition 4 times. But our idea was to uncouple simultaneously, or let's say, potentially simultaneously, 5 different materials. So water, calcium, iron, barium, and gadolinium, where the contrast agents are in these cuvettes, and the calcium and water are in this plastinated mouse phantom. So we acquired all those energy beams, as you saw, and then we plugged it into some denoising plus decomposition algorithm, and we could quite happily extract all these 5 materials, generating a multi-material map with 3 contrast agents, bone components, and soft tissue components. And not only we could separate the elements, but we understood that we could still retain a quite good quantitativeness with errors in the order, I would say, maximum 10–15% from nominal to measured concentration of contrast media. And this has been just published in Optics Express. On the other end, okay, so that was detector-based, sorry. And to sum up the spectral imaging part of this talk, I would like to compare crystal-based and detector-based systems. So, of course, with crystals, you have a higher energy resolution with respect to detectors, plus you don't have all the messy spectral response. Both systems are in for multiple material decompositions with some differences, though. The sensitivity is, of course, the best. We argue it's the best for crystal-based systems, and as always happens with crystals and synchrotrons, but crystal-based systems are very complex with respect to the detector, and they are available only in synchrotrons, whether the detector-based systems, you can use it basically everywhere. So enough with spectral. I'm going to move on to phase contrast now. So I think this you know very, very well, but still, phase contrast imaging means imaging phase effects. And first of all, we should understand what phase effects are. And in a super simplified model, so yeah, the physicists among you will pardon me, hopefully. Phase effects for me is just refraction. And refraction is due to changes in space of the real part of the refractive index. And it turns out that for soft tissues, refraction angles are in the order of 1 to 100 microradians. So these are very small angles, and that's why we don't see, let's say, phase effects if we have if we don't use some method to highlight these angles. And there's another effect that can be interpreted as multiple refraction. So basically, it's just the same as refraction, but with multiple sources. And this is called ultra-small angle scattering or dark fields. And in this case, you don't have a deflection of the beam, but you have a diffusion of the beam. So the beam gets wider, let's say. And also the diffusion is dependent on the properties of the sample and gets in the range 1 to 100 microradians. So as I told you before, phase contrast imaging means transforming these two effects into intensity modulation on the detector. And of course, there are many phase contrast techniques. I'm not going to mention all of them, and for sure I'm missing some, for instance, ghost imaging. But I want to stress that all of them have been pioneered at synchrotrons. So synchrotrons are the place for phase contrast imaging, and they have a lot of pros, of course, and actually the main pro is the brilliance, of course, that allows you high spatial coherence, so to work with quasi-ideal plane waves that are perfect for phase contrast. The high flux allows you either to go fast or to pick a very narrow energy range, so to go monochromatic. And synchrotrons come in all sort of shape and size. Shape is always round, but yeah, different size and sources, so you have broad energy range and you can do many applications with it. And I think they are and will be the ultimate benchmark for development of new techniques or for pushing the existing techniques to the limit. But on the cons side, there are huge infrastructures, few in the world, and expensive to build and run. So the real challenge is to try and downscale things from a synchrotron scale, 100 meters or more, to lab or hospital scale, to 1 to 10 meter scale, let's say. And of course, I think at least in a simplistic view, there are two paths towards downscaling. So either you develop compact synchrotron-like sources, so you just change your X-ray source and try to use the same techniques you are using at the synchrotron, basically. And this has been accomplished with some degree of success by liquid metal jet anode source or by inverse Compton scattering sources. Or on the other end, you try to adapt your technique to work with existing X-ray tubes, basically. And for doing that, you somehow need to structure your X-ray beam and analyze locally perturbation introduced by the object. And we have got very successful examples of these. Of course, there's Talbot grading interferometry, there's speckle-based imaging, and there's edge illumination imaging, which is what we are doing in Trieste. So a couple of examples of propagation based at the synchrotron. Of course, you are very familiar with that, so I'm gonna go pretty fast. So as you might know, also in Trieste at the CIRME beamline, we've got we performed a lot of studies for a clinical study of breast CT, and one of the first thing we did once we had all our setup and our optimization, we tried to assess quantitatively the difference of image quality between a conventional breast CT scanner at the Radboud Medical Center in the Netherlands and our setup, provided that the dose to the patient was the